Go ahead, Joshi.
All right. Um, Hello, everyone. My name is Jiaxin Liu. I'm a master student and major in mechanical engineering. My concentration is the thermal, fluid, and energy. And today I will talk about my work progress on the special problem in ME, which is also called ME 800. My topic is 2D materials application on the thermal management, and my instructor is Professor Xian Zhang. And the first is the outline of my presentation. There are five aspects. The first thing is the general introduction, and the second, we will have a project vision, and third is the theoretical analysis, and fourth is the modeling and the simulation. And finally, we will get an outcome and the future work. So first, I will give you a general introduction about my work. The first thing is the thermal management, which is also on the bulk area. So what is the thermal management? The goal of it is to control the working temperature of objects, such as this figure. You can see this is a CFD model of electronic devices. And what is the methods for the thermal management? There are two. The first is temperature monitoring, and the second is device cooling. And what is the directions? The first is the cooling system, which is very familiar for us. For example, the fan on the electronic device and heat pipe as a heat exchanger. But in my project, the topic is on the thermal interface materials, which is shortened by the TIM. So as you can see from this figure, when there is several surfaces, between it tends to be some air, which is also called the contact resistance. Because of it, it will have some temperature indifference. We all know that air is a poor conductive materials, so it tends to be a high difference into this heat sink and the chip, which will lead to heat failures when there is some bad scenario. But with the TAM, you can see here, the temperature difference is lower by the high conductivity compared with the air. And this is the topic of my project. After bulk areas introduction, we come to the macro scale. What is the 2D materials? The definition of it is the crystalline materials of a single layer of atoms. Here is a basic type of 2D materials, and in my project, the admirable properties is as three factors. And the most important thing is the ultra-high thermal conductivity. And the second additional properties is the mechanical properties and the tunable physical properties, such as the electricity insulation. And I will give you brief examples on the performance of these 2D materials. Compared with the diamond, which have a high temperature, high conductivity, about 2200 watt per meter per Kelvin. The graphene and the cubic BAS have a similar amount in scale. So after we get such introduction, we will think the project vision. So in my vision, I will build on a bridge of these two work. There are two words I mentioned before. So why we need such a bridge? There are two reasons. After we have some macro scales research on 2D materials, we need an application direction for these research results. And because the conventional macro scales heat management design are based on the designer's experiments or their experiences, so we need a future direction for it. Because we all know that with the advantage of the 3G, 5G communication device, the power will become higher and higher. So the thing we need to think about when we designing such heat management heat sink or other devices, we need to think about the macro skills principle. And in my project, the bridge is the 2D materials applied in the TIM, which is the thermal interface materials. And there are two technical paths. And the first is the feeders for the conventional polymer-based TIM, and the second is the replacement of the polymer-based TIM with the 2D materials in 3D assembly. So here you can see a basic structure of electric devices. So in different parts, for example, between the chip and the heat spreader, and between the heat spreader and the heat sink, there are TIMs between it. And just like I have mentioned before, the TIM can cut the difference of the temperature. And how to build such a bridge? There are several steps. The first step is to select the prescribed materials, and after that, we will model the heat dissipation to see a visible heat dissipation process, and then we will explain the misalignment between the macroscale's property and the bulk process. And then we come to the optimize our materials and structure. After that, we will come to the validation. And the toolkit of my project has three aspects as follows. The first is to calculation about the heat conductivity. For example, via some software like the Media Wasp and the LAPS. And the second is to modeling and simulation. And it is also my current work. It has been achieved by the software like the Console and Excel and MATLAB. And in the future, when we come to the optimization work, we will use the MATLAB and Python for my achievement. And with this vision in mind, we'll come to the theoretical analysis. The first thing is the macro scales. How to get heat conductivity of a perspective to the materials. So as this equation, you can see that the different variables in the equations are labeled here. So with this variance, you can get a conductivity of 2D materials, but so you should keep in mind that this is a macro scales heat conductivity, but it is not in the bulk. So the related theory here will include this 4 area. And after this, we come to the macro scale ground, which is built on the heat resistance. So here is abstract model about the heat generator and the heat dissipation. From here, you can see in the Z direction, there are 2 different paths. The first is the upward path. The second is the downward path. And in each path, there is a constant heat flux. And with it, we can get this equation. With this equation, we can get some temperature profile of each part. And here is the temperature profile of the heat generator. It tends to be the chip. And we make an assumption on the symmetry at the Z direction. And with it, we can have some special heat resistance formula. For example, for the conduction, convection, and contact. After we have this theoretical base, we'll come to some initial calculation. Here, in different parts, I made some calculation on the heat resistance and also includes the convection. After that, you may think, so what is the exact heat generation in one system? Could you have some visible mean to show that? So we make some modeling on it. So first is the system layout. From this view, you can see the different color means different materials in the system. For example, the PCB board and the connection between the chip and the PCB is the solder bore area. And here is the substrate, and here is the end field. You can also regard it as another kind of TIM. And here is the D as a die, which generate the heat power is around 50 watt. And after that, here is the TIM between the heat spreader and the die. So we neglect the heat sink here. And after we have such a system, we come to the simulation based on that modeling. And here is the temperature field of it. And you can see here, when we come to the XZ view, the different color shows the different temperature in this system. So the most brighter one means the higher in temperature. So you can see because we have a deep a low heat conductivity of the TAM, temperature here is much higher than other parts. So when we come to a specific area, you can see from this picture, the x-axis stands for different distance of the part. For example, here it means the PCB, and here means the DIE, also the chip. And from here, you can see because the conductivity is different, the heat difference will become various. And you can see here, the scope is much steeper in the TAM's area, which means in such place is the key to heat removal. So with this in mind, we will show a comparison on the different scenario. So here is a comparison on 3 scenarios. The first is the conventional TAM, which is the polymer-based TAM, and the second is the green line, which is the graphene, and the carbon nanotube, which is built on the 2D materials, and the third one is the air without any TAM. So just as I mentioned before, if there is only air between the surfaces, the temperature will become so high that the local point will become a heat spot, and it will lead to the heat failure of the device. So it is not accessible. And after we come to the TAM, we will have a zoom view. From here, you can see when we use the conventional TAM, the temperature difference between the chip and the heat spreader is around 10 degrees in Celsius. But when we change to the 2D materials, the temperature will lower than the 55 degree, and the temperature difference will lower than the 2 degree. So from here, you may have a concept on the 2D materials performance, and then you may think, so what is the exactly role played in the 2D materials as a TAM when we come to think about the material or the structure? So after that, I made another modeling, which is a detailed view on heat transfer in the TAM. So here, I used the first technical parts of the 2D materials as a TAM, which is a filler of the conventional materials. So here you can see a bulk of the rectangle board, which is the whole TAM area. And in this tiny point, there is an example of the 2D materials filler, which is like a honeycomb. And you can imagine around here is a block, and which is the polymer-based TAM. And between this such a unit cell, the honeycomb played as a feeder. So when we change the honeycomb's structure or the material, such as the volume fraction and the pressure, put pressure on it, the heat conductivity will change as we make some change on some factors. And this is my next step simulation. So above all is my major work on this project. And here we come to some results. The first is I study on the theoretical principle in macro and macro scale. And second is I model the box system and get some dissipation and to find the key to the heat removal, which is the TAM, the thermal interface materials. And then we come to build the detailed unit cell, which is for our model next step simulation. And for the future, I will fix on the simulation on the TAM unit cell and make some evaluation based on some factors and optimizing the macro structure and materials. And finally, the final goal of my project is to have a systemization of the whole process into a framework. So I think in the future, the design of the heat spreader or the heat sink will become a problem with such similar descriptors as I just showed. So I think my work will become like a systematic framework for the future's design. So this is my work. Thank you. Any problem?
Okay, we'll open it up for questions. Yeah, I think that was a perfectly timed presentation. Thank you. Questions from anybody from the audience?
I have a question.
Okay, go ahead.
Can you go to the slide 10, number 10? I just wanted to know what is the unit of the temperature. It seems that the temperature is very low. Is it Kelvin or degree Celsius?
You mean?
Because here you write K, so the temperature seems too low. I think like 40 Kelvin is something very low.
Sorry. The real temperature is shown here is the Celsius in degree, and maybe there is because I make this figure based on this part, and I think maybe some arrow in here, but the real thing is here shown in the Celsius in degree.
Okay, I get it.
So Xiaoxing, is there any kind of with this thermal management type of device? Is there any kind of experimental work that either you or somebody in your group is working on, or that maybe will complement or validate some of this model?
Actually, because the campus is closed, my initial plan is to make some validation on this structure because I have took some the MEMS class in the last semester, but I think in this situation I have to do some simulation and modeling work. But I think maybe in the future I will make some validation. And you know that I am from the Professor Xian Zhang's group, and her group will fix on the metrology of the 2D materials. I think it may become some explanation on my simulation results.
Okay, the other thing I wanted to ask is if you just stay on this slide, and then I noticed in the design, I guess it's from basically from 0 to 4 millimeters, right? Approximately, that's the range of your height. That's your height here. Approximately 4 millimeter.
Here you can see height. The height of the TM is around 0.17 millimeter.
0.17 millimeters. So you mean about 170 micron, right?
Yes.
How many layers is that?
To talk about the TM, I think you can see here. I have built on another details model on the TM. So I think to talk about the layers, I mean the 2D materials is such like some nanometers in one single layer. But when it comes to the bulk area, I mean it will become in the scale of the 40 micron, I think.
Okay, so when you're modeling this kind of honeycomb structure, each one of these unit cells, you're saying that the height of this is 40 microns?
You can see here, when I use this modeling, the extrude is around cell model here.
About
40. It's 40 micron.
Okay.
And this is another question I want to validate in the future because in my last model, I want to use some thin layers thinking in it. But after I read something about the nanoscales heat transfer, I mean, the temperature limit is around, I think it's 50 micron. But I think when we talk about the bulk areas model, even the small height, the small distance is larger than that limit. So I think in such bulk area, there is no link with the macro scales heat transfer. But if we delve into the unit cell, I think it should be considered the heat transfer in nanoscale. I think this is one key point for my future work.
Any other questions from the audience?
I just had one other question. Can you explain how is the manufacturing of such a small 2D material? Do you have any information on that? How they fabricate such honeycomb structure, which is very small? In what technology they use?
You mean the fabrication method for the 2D materials?
Yeah.
For example, when we build on such like the graphene, you will use a means like called the mechanical expolification. Just like we tear up the tape, we tear up one layer one time, and the layers of the graphene will become will form the graphite. And when we use this mechanical expolification, I don't know whether I pronounce it right, but I will show you in spelling later. But this is one way. And the other way is to use the CVD, the chemical vapor deposition. So this is another way. And if you can go to the website of the Professor H. Yang, he has some research on this part. And I think maybe it can answer your question more clearly.
Thank you.
You're welcome.
More questions? Let's move. I guess one thing I wanted to ask, I guess before we wrap up here, is your selection of 2D materials. Is there a reason why you decided to model, I guess, graphene here, or what is the rationale here, and what is your kind of target here? Does the material come into consideration, or does it matter? And how will your model diverge depending on the material selection?
So there are some factors that must achieve when I want to use 2D materials. The first thing is the ultra thermal conductivity, which I have talked in the first slides. And the graphene or the cubic BAS can achieve such requirements. And the second thing is to fulfill such like the electrical insulation. But in that way, I mean, the graphene will not conduct admirable materials because it's conductive. But if we can use this graphene as the as a feeder of the polymer-based conventional materials, it can hold water. But I think, just like you see, there are some factors that I need to consider when I choose these materials. But the most important factor is the thermal conductivity. And right now, my selection is based on one paper that is in that paper, the researcher put forward such like the graphene and the cubic BAS as an candidate for the 2D materials.